Welcome back to chapter 12, nervous tissue. This is video number 12. So here we have a bigger version of the same graph that we saw on the previous diagram. So now we're going to take a look at what an action potential involves in the different periods. So -70 is the approximation for the resting membrane potential. So that's the difference in charge between the outside and inside of the neural cell. Now, right here is our threshold value. Notice that it's not very far up on this graph. So it doesn't take a lot to reach threshold. So this right here represents the graded potential. But once that graded potential reaches this point, then we can see a huge, sharp increase in the millivoltage, the difference, the potential difference, and we end up going up past 0 to about +20. So this phase is called depolarization. Once we reach the top and those sodium channels start closing, potassium are still open, so we end up with repolarization. So over here, this side is sodium driven. This side is potassium driven. So that's what drives these different phases. This is one reason why sodium and potassium are really needed for your body to work properly. If you get dehydrated, you end up with lower concentrations of these because these also come out in your sweat and you don't work as well, which is why people drink sports drinks because they have these electrolytes in them. So once we come down to this point, when we're down below the resting membrane potential, this little part right here is our hyperpolarization. And sometimes this area right here is called after hyperpolarization, but I'm not really going to require you to know that. So once we get down past here, we end up with hyperpolarization. We go below, we make this difference a lot bigger. The other thing that you see here is something called a refractory period. It's like a reset. This is a decrease in sensitivity to further stimulation after an action potential. So this is like a reset. And it's broken into two parts. You can see absolute and relative. During the absolute refractory period, we have complete insensitivity, which means no action potential can be generated. So this is a complete reset, so nothing can happen. We cannot generate another action potential during this period because everything is functioning. This guarantees a complete action potential. So remember, it was all or none. So this helps us with our all or none principle. The second part of that refractory period is the relative refractory period. Here we can generate another action potential if we have a stronger than threshold graded potential. So if the stimulus is so big and we generate a really strong graded potential, during this period, we could get another action potential. But only if it's really strong. So just to reiterate the all or none principle, because it applies here, it's due to the absolute refractory period. And it basically states if threshold is reached, an action potential happens. There's nothing to stop it. It happens, and it's going to be complete because of the absolute refractory period.